But let's talk now about how inductance is calculated. And this is another one of those opportunities to talk about how in sort of conventional physics classes, when you talk about inductance, you often set up integrals and find analytical solutions. And of course, in the real world, that really only works for a very small number of cases. In reality, these are usually solved numerically, where you allow a computer to solve it. Maybe you have to set up the integral for the computer, but the computer is actually going to be solving an integral by adding up a bunch of small distributions in sort of discretized space. But let's kind of see how this works a little more intuitively. So the steps to calculate inductance basically are going to take 4 steps. But before I get to that, let me just sort of review the idea of inductance as basically being like an engine that's generating magnetic flux lines through a surface, right? So the higher the L is, the stronger that engine is at turning currents into magnetic field lines. And so that's how we got this relationship that that the flux density phi equals L times I. So L is a measure of how good our engine is at turning currents into magnetic fields. Magnetic fields store energy, so there's a little bit of energy storage is happening here. It's how good is our engine at turning currents into storage of energy in magnetic field lines. All right, now oftentimes you'll see this written in some form like this, where there's an N right there. And N sometimes is, let me just put all that in blue since it's technically a little bit different. And N, sorry, the N would be over here. The N would be number of turns, since oftentimes in inductors, you'll take a single wire and you'll wrap it around a circle many times. And I would refer to the current that you're running through one wire, but you're wrapping that wire around some number of times. And so you're getting a multiplication factor of N. So sometimes it's written like that. So for example, if you have a coil of wire like this, and you're putting a current I through it, and there is N number of turns, you could think of the total current, the effective total current, as being N times I. But oftentimes in this equation, I just represents what you're putting into the current in one location, not the sort of total current that's spinning around in a circle. All right, so you may see it in either form as long as you're clear on which one it means. All right, so the way you calculate inductance basically has 4 steps. The first is to assume a current, I. Step 2 is to calculate either the magnetic field or the magnetic flux density that results from the currents. That's step 2. Step 3 is to calculate the total magnetic flux inside a closed path, right? So you've got to pick a closed path that has current running through it, and then you're calculating the magnetic flux accordingly. And then 4, you're just dividing phi by I, the current, right? Because we can take this equation right here and rearrange it that L equals I over phi. Right, so that makes it relatively easy. All right, but of course, there's a very small number of problems for which you can actually solve this analytically. And you know, some of these we've already seen, even though we didn't talk about how you get these answers, but we saw this way back when we were talking about transmission lines. That, for example, for a parallel plate, we can define the inductance as being mu. Mu is the permeability times d over w. D is the distance between the plates, and w is the width of the plate. We can do this for a coaxial cable. We can do this for other geometries of transmission lines. And let's just say that these are solved analytically, but the number of problems that you can solve with an analytical solution is relatively small. And so it's not really worth describing how you do that. However, I will sort of set up one example just so you can kind of look at it in the notes in case you want to, right? And this is a classic example that you found in any physics textbook, something called a toroid. And this is how many inductors are formed, sort of standalone inductors that you might put on a circuit board, for example. And that simply consists of a sort of a donut shape, and around that donut shape, you're wrapping a wire many times. And the donut shape is assumed to have kind of a, either a square or a circular interior that has, length or diameter h. And so a classic physics problem is, what's the inductance of the toroid? And that's one thing that you can solve relatively easy with, analytical solutions, since you know what the magnetic field from a wire is. The details of how you do that is in the notes, so I won't kind of go through that right here. But this is kind of one example. But again, there's a limited number of cases that you can actually solve here analytically. I think the more important thing is to understand what inductance means. And again, inductance is the ability for currents to generate magnetic flux lines as a result of that current, right? The higher that ability is, the higher inductance you're going to get. And the reason that's important is that inside those magnetic flux lines, you're also storing energy. And that's really the most important part, is that inductance is a mechanism to store energy in the connection between currents and magnetic fields. And so in the next section, we're going to talk about what it means to have magnetostatic energy, or energy stored inside magnetic fields, and how we actually calculate that.